My name is Alireza Mahzoon. So, yeah, it's okay. No problem. Yeah. I'm part of the Infineon DFX team, and we are working mainly on the DFT flow and DFT execution for the automotive chips. So I prepared this presentation with my colleagues Xiaojun Shao, and it's mainly about the Tessent Quick Synthesis and how we take advantage of it to find these RTL issues in early phases. We all know that Tessent DFT RTL is a very powerful and important tool in the DFT flow. It gives us a lot of flexibility in insertion of different DFT instruments with different configurations. You can insert an EDT, set the number of input-output channels. You can insert different types of OCC. You can insert a standard OCC, synchronous OCC, parent-child OCC, and many other instruments. And you can set many configurable parameters for these instruments, maybe hundreds. And it gives you also a lot of freedom in modifying RTL. You're free to add a connection, remove a connection, or even add some new logic to your RTL. However, with this flexibility and freedom also comes responsibility. We have to make sure what we did in the DFT RTL insertion is correct. Fortunately, Tessent already provides us with some verification patterns. For example, we have this IJTAG network patterns, SSN patterns, MBIST patterns, and we always simulate them. And based on that, to some extent, we can make sure that what we did during the DFT RTL insertion is correct. However, usually simulating these patterns at the RTL level is not enough to verify everything. There are some issues that you can only catch them during the ATPG or even later during the gate simulation. However, it's usually too late because in order to reach the ATPG, you have to go through synthesis. It might take hours, days, and it also wastes a lot of resources because if you reach the ATPG part, you realize something is wrong, you have to go back, repeat everything, and of course, you waste a lot of resources as well as time. Now it raises an interesting question. Is there a way for us to verify the DFT RTL insertion in an earlier phase? So the answer is yes. We can take advantage of the Tessent Quick Synthesis. So in this presentation, I want to explain how we integrate the Tessent Quick Synthesis inside our DFT flow, and we use it to verify the DFT RTL insertion. So I start with 5 questions. What is Tessent Quick Synthesis? How we run it? How long does it take to run it? When is the best right moment to run Tessent Quick Synthesis? And why is it important for us? And at the end of my presentation, I also bring up 3 use cases that Tessent Quick Synthesis help us to catch some problems. So what is Tessent Quick Synthesis? So we take advantage of Tessent Quick Synthesis to generate a netlist out of RTL. In order to do it, you need input. So the input for us is the TSDB, Tessent database, which already contains the RTL, modified RTL. And the important things about Tessent Quick Synthesis is that usually it's much faster compared to the real synthesis, which is done by physical team or a synthesis team. Orders of magnitudes faster. And it has some features. It supports multiprocessing, which speed up the process. And of course, for the synthesis, you need cell libraries. We take advantage of the RTLC cells libraries from Tessent. But it's important to know that what we get out of Tessent Quick Synthesis is a dummy netlist. It's not a netlist used by other teams. It's only used by us, DFT team, for the verification purpose. So next question. How to run Tessent Quick Synthesis? So there are 8 steps, or at least we use these 8 steps to run the quick synthesis, get the netlist out of it. They're very straightforward. So the first step is optional. You can set some multiprocessing options to speed up the whole process. You need to set the context to DFT RTL. Particularly, this one is important. And then you read the cell library, in our case, the RTLC cells from the Tessent. you need to open all these TSDBs. It might be one TSDB. In some cases, you might have these nested TSDBs. You need to read everything in order to have the whole RTL. Then you can generate the full netlist, basically. Then you read the design and set the current design. You have to set your top module because you get finally the netlist for the top module. And then there's some options that we set for the quick synthesis. We want to get the full netlist. So we set the complete synthesis to on. And there is another option for synthesis of 2D arrays. We set it to unlimited. It increased the runtime, but eventually we want to get the full netlist. So we have to set it to unlimited. Then you enter the analysis mode. The tool already starts to run the synthesis. And finally, you can write out your netlist as a Verilog file. So the next question, how long does it take to run Tessent Quick Synthesis? As I said, it's orders of magnitude faster than the real synthesis, which we run it later. I did some experiments on our server for two design. One is a smaller, basically two partition, I can say. It only have 4.1 million gates. Another one is bigger, 8.2 million gates. And on our server, if you don't use multiprocessing, you can run it in roughly 12 minutes. If you activate the multiprocessing, it's slightly faster. Also for the second design, to note that it also has many 2D arrays, basically. So the runtime is bigger. It takes roughly 30 minutes. And with multiprocessing, is slightly better. So you see, in 30 minutes, you can get a netlist out of this TSDB. And in all our cases, it usually takes less than 1 hour to get a netlist, which is a big advantage. The next question, when can we run the Tessent Quick Synthesis? So the input to the Tessent Quick Synthesis is the TSDB. So whenever you have a TSDB, you can run the Tessent Quick Synthesis. Usually we break the RTL insertion into 3 phases. So first phase, we call it RTL 0 or pass 0. We don't run any insertion in this phase. We just read all these RTLs to make sure everything is consistent. And we create something called pre-insertion TSDB. Then we continue with the pass 1 IJTAG MBIST insertion to create pass 1 TSDB. And eventually we insert the rest of the DFT instruments. And then we get the final post-insertion TSDB. So basically you can get a netlist after each step, based on the TSDB you feed into the Tessent Quick Synthesis. In our cases, we usually do it for the first one, pass 0, to do some tracing if necessary. We rarely do it for the pass 1, usually not needed. And of course, more importantly, we run it after we have the post-insertion TSDB to run some verification, make sure what we did during the RTL insertion is correct. So then comes to the important question. So why is the Tessent Quick Synthesis important for us? As I said, we run the Tessent Quick Synthesis in pass 0 when we have the pre-insertion RTL. But why is the reason? So sometimes we need to trace the RTL. And this information might be used during the insertion. However, there are some limitation with the tracing RTL. It's not always complete. Means that if you have some complex RTL parts like generate a statement in Verilog or VHDL, the tool cannot go through those parts. The tool stops at the boundary of those generated statements. In addition, some of these advanced tracing commands like trace flat model is not, of course, available during the RTL. However, if you synthesize the RTL and get a netlist, then all this generated statement will be accessible because everything gets synthesized to some logic. So you can use, for example, get fanning, get fanode. You're sure it does not stop in some blocks because everything got synthesized. And also some more powerful commands like trace flat model can be used in this case. But there is also a more important reason, as I mentioned, to hunt this DFT RTL insertion issues before synthesis. As I said, after having this post-insertion TSDB, we again run the Tessent Quick Synthesis to get a netlist out of it. So the problem is that when you run these verification patterns, you cannot catch everything. So we need to use this netlist and somehow reach the ATPG part in order to find these problems that might occur only during the ATPG. We can catch them only during the ATPG. So this running RTL simulation, probably LEC, to make sure you did not mess up with the functionality, they are not usually enough to make sure everything is correct. So especially there are some specific problems like wrong instrument, DFT instrument configuration. You might insert some TDRs, but you miss to connect it to some parts of the logic, or you connect them incorrectly, these TDRs. Or there might be some RTL issues which might affect later your ATPG, result some DRC errors during your ATPG. What you want to catch them probably earlier and probably give feedback to the RTL designers. So as I said, we use the Tessent Quick Synthesis, but how we do it? So when we run the DFT RTL insertion, after finishing get the post-insertion TSDB, we run the quick synthesis. We get the netlist, we run through a scan insertion using Tessent, and then we can run again also ATPG. So we have this full DFT flow, but with this Tessent netlist, basically, we get out of the quick synthesis. To further clarify this, so here is the traditional, like let's say DFT flow, that we first run the RTL insertion, DFT RTL insertion, say pass 0, pass 1, 2. We get the post insertion TSDB. Then we have to run through. So in this step, we usually release the TSDB. So the other teams get involved. For example, synthesis team get involved, or physical team to run the synthesis for us, and also other team might verification team get involved to pick up this modified RTL to do some verification. However, if we find out there is a problem in the RTL, again, we waste a lot of time, a lot of resources. We have to go back to run the RTL insertion again. However, we can, as I said, we can integrate the Tessent Quick Synthesis into flow to avoid such problems. But how we do it? So after having the post-insertion TSDB, we run Tessent Quick Synthesis to get the pre-insertion netlist. Then if any tracing is necessary, we try to do it, and this information will fed back into the RTL insertion pass 1 and pass 2. It might be used by this pass 1, pass 2 insertion. More importantly, after having this post-insertion TSDB, we again run the Tessent Quick Synthesis. We get the post-insertion netlist. As I said, we run the Tessent scan insertion to get the scan inserted netlist. Then we run the ATPG. Of course, we don't want to run the full pattern generation. We just generate part of the pattern. For example, we can generate 64 patterns for the stockhead and, for example, 64 pattern for transition. And then you can even run the simulation. So you have a subflow now. Then you check. If everything goes well, you don't get any error. For example, you don't get any DRC error during the ATPG, and or your simulation also pass. Then you say, okay, everything is fine. Now we can release or modify it RTL or TSDB, post-insertion TSDB. However, if we find out there is a problem, we can easily debug it. We can find out the source of the problem, and if comes from the RTL insertion, we can go back and fix it. So, and the whole thing is very fast. Maybe in few hours, you can perform everything, and you can already try the ATPG, make sure everything is working. I have some basically use cases for this quick synthesis flow, or this proposed flow which integrate the Tessent Quick Synthesis into the DFT flow. The first one is about tracing RTL, as I mentioned. So there are some complex RTL parts like generator statements, which the tool, during the RTL tracing, the tool cannot easily go through them. For example, here we have a generator statement which creates some clock gates. And for any reason, you are interested to find these clock gates in your RTL. And probably you want to add clocks or do something with them. However, if you use some Tessent command, like get fan out or get fanit on the RTL, it directly stops in the boundary of this generator statement. So you cannot go through this generator statement. So you cannot fully trace the RTL. However, if you synthesize everything using Tessent Quick Synthesis, then everything gets synthesized and everything will be accessible. So you can easily, after having the netlist or after synthesizing the RTL, you can use the command like get fan in, get fan out to go through this, for example, generate a statement, or even use more complex or more advanced tool command like trace for flat model. I have another example. So it's about rank DFT instrument configuration. So for example, assume that you want to insert an EDT into your design. It's the correct configuration for an EDT. So you want to insert an EDT with 30 input channel and 30 output channel. However, by mistake, someone set it to 3. So what happens is that you are using a very high compression here for this EDT. So if you use the right configuration and try to run the ATBG, you go through Tessent Quick Synthesis, scan insertion, and ATBG. So you expect to, at least with 64 pattern, you roughly get 50% stochastic coverage. And if it happens, everything is okay. However, if you use the wrong configuration and try to run the ATBG, you get a very low coverage because you are using a very high compression in this case. And then it's alarming. You say, okay, there is a problem in my coverage. I have to go back and see my DFT spec to see where is the problem. And then you can go back, find it, and solve the problem. There is another example related to this wrong DFT instrument configuration. It's about missing on-chip compare. So on-chip compare is one of the SSH or SSN features, and you can set it in the DFT specification and insert it along with the scan streaming network. So it's the right way to do it. But for example, DFT Engineer, for any reason, forget to do it. So forget to insert the on-chip compare. And it's something you are going to use during your, for example, ATBG pattern generation. So if you insert the SSN correctly, and during the ATBG, you try to set it to enable, you try to enable the on-chip compare, everything should work correctly, and you should be able to generate patterns. However, if you forget it and then try to set it to enable during the ATBG, of course, it doesn't work. You get directly error during the ATBG. And then you say, okay, there is no on-chip compare enabled. Probably forget to insert on-chip compare. Let's go and fix it. I have another example. It's a more complex one. It's related to missing TDR connections. So we are in our designs, we use the Tessent OCC. When you use Tessent OCC, you have basically two flavors. You can either insert the TDRs for the OCC directly inside your OCC, or you can bring them outside your OCC and then connect these TDRs to the OCC. So they are outside the OCC. We tend to use the second option because in this case, you can share these TDRs between different OCCs and you have less smaller number of TDRs, and probably you cut your setup time. However, you have to be careful about connecting these TDRs to the right input of your OCC. If it happens that for any reason you forget forget to connect this right TDR to the right input of your OCC, basically it fails, your ATBG fails. So here I have an example. So we're supposed to insert a TDR to control the fast capture mode of the OCC. But for any reason, we forget to insert it, or we missed it. And what happens is that in the RTL, the tool tie this fast capture mode to 0. So when you run the stochastic ATBG, you don't get any problem because it's supposed to be tied to 0. However, if you want to run the at speed or transition delay ATBG, so you try to set the fast capture mode to on, but already you get an error that, okay, it is tied to 0. It's impossible to basically force it to 1. So you can realize, okay, there is a problem. You can easily find the problem and go back and fix it during the when you're on the RTL insertion. And okay, now I want to just conclude my presentation. We believe that Tessent Quick Synthesis is a powerful tool. We can use it for tracing RTL, particularly when we have the pre-insertion TSDB. And we also try to verify the DFT RTL insertion. when we have the post-insertion TSDB. And we try to integrate it into our DFT flow in order to avoid these RTL issues. And yeah, with integrating this Tessent Quick Synthesis into our flow, we can save time and resources caused by these RTL issues. Of course, we also find out some problems with the Tessent Quick Synthesis. We try to report them to Siemens EDA. For example, one of these problems was related to the system Verilog interfaces. So we realized that the tool behaves a bit strange. It cannot synthesize the system Verilog interfaces correctly. We already reported, and we also find some minor issues, but we already reported them. And we hope that Siemens EDA continues supporting this Tessent Quick Synthesis and try to even further improve it. And yeah, at the end, I would like to thank Siemens EDA, particularly Rolf Sommers and David Mena for their continuous support regarding this DFT topics. Thank you.